first debate is on the design of service courses in undergraduate mathematics. So welcome Chantal, Becca, Chester, and Miro. I think because Peter is not here yet, could you introduce yourself to the audience briefly? And then Chantal will kick off the debate with your opening statement.
Yes. Hello, I'm Chantal Buteau from Brock University. What is to say, I've been there for about 20 years, 21 years to be exact. I have taught practical statistics and practical calculus service courses a few times, more the stats than the calculus. And the last time that I did teach the calculus was about 10 years ago. But I have been involved in our departmental service course committee over the years. So I've been keeping in touch with what is going on. Maybe the last thing I want to say is, no, I'll just leave it like that for now. Yeah, and one last thing. For me, service courses mainly means our main service department is business and also sciences, but it's mainly business.
Hi, I'm Becca. I'm a PhD student and teaching fellow in the Department of Math and Stats at Queen's University. During my PhD, I've taught a couple of service courses. I've taught calculus, linear algebra, and as well as statistics and differential equations for engineers.
Hi, I'm Chester Weatherby from Wilfrid Laurier University. I've been teaching for nearly 15 years now at the post-secondary level. I've done service courses, I've done focused pure math classes all the way up to senior, fourth year level grad courses. I do have more of a primarily teaching role at my institution, where I have a heavier workload on teaching focus, less of a workload on research, which gives more time for teaching considerations. And along with that, I've had many opportunities to teach service courses to sciences, business, and so on.
Good morning. My name is Miroslav Lovric. I'm from McMaster University, and I've been teaching for a very long time. Actually, if you add up the years that actually other people have taught, then that's less than what I've taught, so probably. And I've taught every single possible course. So in many ways, I feel comfortable debating this and opposing everybody else's views, as Kitty pointed out. And one other thing is that yesterday we were competing with Metallica concert. So that was actually a pretty big sacrifice that some people were here, I guess. Yeah, that's why I wasn't here, exactly. I told some people I was ill, but that's just an excuse.
Okay, thank you. Welcome. So Chantal, you kick off the debate with your opening statement. Over to you.
In brief, my argument is that, well, students are changing. Digital technology, including generative AI, is evolving rapidly, and we are slow to react and adapt. So basically, in short, we're slow to adapt what we teach, what mathematics we teach, and how we teach it. This argument, you can say, you can think about our math programs as well, but certainly in the context of service courses. When I received the invitation, I looked again at the statement, and it says, can I see it here? We are teaching the wrong things. Then I thought, is it asking me, are we now teaching the wrong things? Or is it asking me, are we still teaching the wrong things? The debate, we agreed, the debate took place 10 years ago, 15 years ago, and we can think that debate will take place again in 10 years or in 15 years, right? And it's okay, and it's healthy. We should never stop thinking about the relevance of what we teach and how we teach it to our students. What could be interesting is to think, what were the arguments in that debate from 10 years, 15 years ago on both sides of the statement? Which of these arguments would still be relevant for today's debate? Which ones would have become obsolete, and why. So that could as well help us a bit move our thinking about this question. So I'm kind of saying we're sort of teaching the right things. And yeah, I'm not going very on one side or the other side. But for now, I'd like to share a short anecdote. Last year, our service, departmental service course committee reached out to the service departments and asked for examples in their disciplines, in their programs that they would want to share with us so that we can include them in our practical stats and practical calculus courses. And when I say include, that means that we have online modules that are shared with all students enrolled in the course. They have access to it, and so they could be able to access these examples relevant to their programs and disciplines, and there would be labels. They would see right away which ones they want to look at. I'm wondering if with this could be a way for me to check a box to say, yeah, that's kind of support my statement. We're sort of teaching the right things. Or maybe we should ask, okay, these examples are there, but in what ways are they part of the students' experiences, learning experiences in their courses? I'm still not saying how this is part of the course delivery. Is it in the part of the assignments that student will work on? Is it part of the lectures, which are often taught by our part-time instructors? How would they know they should be including these examples? Also, how should we take the fact that a department did not answer to that call? How should we take this? And that takes me to my last point. Who is the we in we are teaching the wrong things? I see the we, the decision maker, the policy maker. I see the we who will be implementing, and I see the we who is assessing right or wrong things. These are not necessarily the same entities. In my view, for the we, for the decision maker who decides, that should definitely include as well faculty from service departments. That should be part together with faculty from math departments to identify what are the mathematical needs for the students. And those faculty should be acting and following up as representative of departments so that it actually goes down to the student's experience. Thank you. That's all.
So this position I'm going to take is maybe not so much that we're teaching the wrong things, but I think that we are missing maybe something in the service courses, that we're not teaching something important. And for me, that's really what it looks like to do math, how we engage with mathematical content and what we're trying to do. And I think that that's not always present in a large way in the service courses. So this kind of arrived, or this point of view arrived from just interacting with a number of students while teaching service courses. And it felt like a lot of them perceived their objective to identify steps, to memorize their procedures, and to replicate them on assessment. And that if they did this seamlessly, they are doing math well. But this feels very different to what I see doing math as. For me, I think math is a structure, and it's a structure that's meant to be understood. And really in that process of trying to understand it, when we kind of grab hold of it, then we can apply it to a variety of contexts and applications that matter to the students. What concerns me maybe about what's happening to students when they're approaching it in this other way is I feel like their experience in the service course isn't really serving them. There's kind of three reasons this sticks out for me. One, I feel like they're missing out on a lot. I feel like they're missing out on a very rich experience that's creative and collaborative. Two, I actually do think that memorizing it turns out to be a harder task in some ways. Like it may seem easier at first, but when you then try and confront other questions and you don't have that deep understanding, it's quite difficult. And three, they're not really developing then those important problem solving skills or those mathematical habits of mind that I think not only help them learn math, but also help them in their other studies and careers. So when I'm reflecting though on this difference of what I see they seem to be doing and what I would hope that they would be doing, I also start thinking about, but what experience are they having? And I realize that a lot of what I would share in a service course is very polished. The results are polished, my solutions are polished. And in that, though that's very important and an interesting part of doing math, they're lacking kind of that insight into the process that got me there and what I did to make sense of it and build these arguments. And that process is really what I want them to be doing. So how can we incorporate that into their own experience? So I guess in summary, I'm not sure if, for me, my position is that we're doing the wrong things, but I feel like we are missing an important part. And that's what it looks like and what the experience is of really doing math. So that's my position.
All right, so I'll probably follow suit here, and then hopefully Miro will rock the boat after me. So I think I mostly disagree with the statement. Actually, I think that we are in fact teaching the right things. At least we can be teaching the right things in calculus or linear algebra or even an intro to proof service course. But it's sort of with a grain of salt, or we have to take the right approach. We have to set it at the right level. So I kind of have a script I'm going to follow here. For me, service courses, the goal is that we're not teaching math majors. So we shouldn't be expecting them to think like math majors and be at the same level of theory and technicality as a math major. So other departments would be chemistry, physics, biology, computer science, data science, psychology. I'm sure I missed some from there. And we want to set those students up with whatever skills that they need so that they can go and use those math skills, whether it's calculus or integration for getting into probability and statistics, and then do whatever they're going to do in their own disciplines. So for calculus in particular, right, we need to understand rates of change so that a biologist can see the interaction between different variables in something they're studying. For probability and statistics, of course, most disciplines have some sort of statistical scientific approach. Psychology comes to mind right away. Maybe we don't need to understand everything that there ever was to know for a math major in terms of integration, but we should have some understanding of what an integral is from a calculus course. So we couldn't just take it out, right? It's still the right thing that we should be at least giving some understanding so that they're not just hitting buttons on Excel, but they're thinking about what they're doing, okay? The next bullet point I have is, now that we sort of know what we should be doing, or what we could be doing, I should say, I shouldn't speak for everyone. Then the approach is, again, to keep in mind that we're teaching non-math majors. So if you're going to set your first year calculus course for math majors up here and you're doing epsilon delta proofs and very complicated limit methods, then you want to make sure you take some of that out. Okay, you want to make it more geometric, more graphically based to motivate things, because that's very easy to understand and apply for somebody who's not necessarily inherently interested in all the theory and technicality of a math class. Okay? Again, they're not math students. So we can pitch it at the right level. Okay, find spots to show theory. Okay, where there's something to be gained from the theory. Short proofs, a little bit of logic goes a long way to help develop critical thinking. Okay, there's also inherently some beauty in seeing that. Okay, often non-math students will say, hey, that was really cool how you in 3 lines prove something or 4 lines prove something. And now they see why the formula that they saw in high school calculus is actually true, because perhaps their high school math teacher didn't actually, explain why something is true, just said it is true. I think there's a lot to be gained there as well. Another approach would be to give relevant examples. I know the argument can be made that it's so easy to lean on physics because we live in a physical world, but you can come up with interesting examples. I think it's something that our institution does fairly well. We're fortunate to have weekly tutorials, weekly labs, and basically problem sessions And we've got hired lab staff that is basically paid to create labs and examples that aren't just the textbook problem, but more interesting and adapted examples that are relevant. Might not cater to everyone, but we kind of pick some from financial math and some from biology and some from chemistry. And so the last is that sort of leaning into how to approach it. It's sort of instructor dependent as well on how they can achieve keeping students interested and engaged. It can't just be abstract the whole time, because people who aren't inherently interested in mathematics might not be interested in just doing mathematics. Something that's helpful is giving anecdotes, historical references, telling stories. That might be the only thing the student remembers at the end of the course, is the story of how L'Hopital purchased a theorem and got his name on it and didn't actually prove the theorem himself, for instance. Okay, and that might reinforce retention moving forward as well. So that helps develop sort of a beauty and appreciation, knowing that it comes from something, helps motivate as well. Now, from the actual departmental side of things, you have to have the right person in the classroom. We have a chance to request courses for our teaching load next year, and fingers crossed you get the ones you want. I often request the first year of calculus in fall term, because I think a friendly face in a first year fall term, the first course that a non-math student might take, it can go a long way. Sometimes, somebody who is so intense on research might not be the right person to be in a room with, 600 non-math majors, because they might not be thinking about, where the students, which level they're at, and how to meet them where they're at and keep them motivated, because the intense researcher is going to be inherently just motivated and think that it's all beautiful. 5 pages of derivation is good, but that's not good for everyone. So, that's up to the chair, up to the departmental committees to make those decisions, to think, who's going to be the best person. 2, 1, done. Okay, all right, I'll wrap it up. So they should think about who it is. And then I guess the last point, maybe the most important one, is that when you're designing these service courses, you have to communicate with the courses that you're serving, or the departments that you're serving, to figure out what do their students need, where are they at, and without doing that, you might pitch things at the completely wrong level. We had this happen with computer science, where they wanted to take away linear algebra as a required course. So we designed a new one, and things are going great now after some discussion. Yeah. All right. Thank you.
Okay. See, one thing when we design service courses, we should think about who is it for? So why are we doing it? And I mean, as kind of history shows, future is notoriously difficult to predict, in the sense that whatever we say today will be wrong. Just think about 10 years ago. How many of you would remember the mention of AI 10 years ago? How about one person? Okay, out of probably 40 or 50. How about cloud architect? How about TikToker? Right? How about content creator? How about data scientist? Okay, so 10 years ago, we were here debating things, and we would have very little, almost no idea what will happen 5, 6, 7, 10 years, right? So rather than thinking about future, let's try to think about all the changes that have happened so far. What survived? What was the thing that never ever changed? And that is, in my view, mathematical thinking and mathematical reasoning. No matter how many changes you have, no matter whether you talk about 1850 or 1950 or 2050, that's always going to be there, right? So in my view, the most important thing about service courses is to teach people how to think, and also how to think within their own discipline. So rather than, for instance, talking about mathematical proof, we should address the nature of evidence. See, for instance, for a mathematician, proof is a proof and has to be redone many, many times. Look at engineering courses. For instance, once people experiment, design, and figure out the best concrete mix for something, it becomes standard, and it is used from there on. New students not reprove anything about that, right? In many, many places, biology, say population biology, you have experiments, you have data, you don't have actual proofs. So to convince a population biology that something is or is not true is actually very much different than writing a proof as you would do, for instance, in group theory. Okay. Related to that is the following issue. On the one hand, we say what has to be done, but what is being done? And why are we having so many challenges? And in my view, the biggest challenge, the biggest obstacle to actually creating a good service course are math departments. I'm talking about McMaster and some other places. You can contradict me if you wish. But for instance, our service courses have to be interchangeable with other courses. So it means that anybody who finishes the first calculus, no matter whether it's for engineering or life sciences or economics, whatever, should be able to switch into any other calculus in term 2, which basically kills your creativity, kills your freedom to do things as you would want them to do. Because if you didn't do L'Hopital's rule in your calculus, actually your chair will be bitching at you because now you didn't cover it and calculus 2 has to start, right? Or if I didn't do trig substitution, well, again, somebody will be bitching at me because I didn't do it, right? Okay. So one thing which is really a huge obstacle is actually we need to change departmental policies. Without it, nothing will happen. We can talk about how, yes, we want to collaborate, but it will not happen unless we gain some freedom in designing service courses as they should be. So for instance, here's one thing. We don't do, many applications that we do are artificial. What about truly authentic applications? See, I wrote a book on math for life sciences. Where did I get examples from? With my colleague, I examined over 200 papers in mathematics, biology, and health. We picked up the math which is there, and that's what we wanted to be the math for life sciences. We didn't find a single L'Hopital's rule. We did not find infinite series, but we found Taylor polynomials. It's very rich in mathematics, but that's not the mathematics which is done in calculus. Okay, sorry? 20 seconds, okay. So authenticity is another problem. And one other thing we should think about is who are our students, right? We always think, and especially in math education research, you think of students as a group of really engaged, willing to learn students who are there because they're eager to learn and they absorb every word you say and are willing to spend 10 hours at home doing the homework that you so carefully designed. Well, that is not true. I want to show hands of anybody whose attendance near the end of the course is more than 40%. Well, where is engagement? Okay, you're the only exception. So when we think about this, we also think about students themselves and not to glorify them, but think about students as we have them today. Thank you.
Thank you for the opening statements. Now we have 10 or 15 minutes for you to interact with each other. Chantal, you can go first because you first.
Well, I will start with Miroslav. I thought you'd be funny, but you're quite serious in your interventions. I'll just react to one, maybe to Becca, something that I heard. You talked about you would like to show the students in service courses about the process of doing mathematics. You did say, I want them to do that, to see that. My follow-up question to you is, do they want to see that? Do the service departments feel they need to see it? And if they see this, what else would you remove from what they are expected to be learning?
Good question.
Although I love presenting process to students, I have to say, sorry.
I don't know if they want to see it. I guess that kind of relates to Miroslav's comment about engagement. I don't know that answer. I do know that they're frustrated when they don't know how to do their assignments. They don't know how to think about them or start them. Maybe that would help. I'm losing track of all your points. One of them was, what would I remove? Time is an issue. I feel like time comes up when thinking about any course. There's not enough time ever, it seems. I think, though, that might also relate to what Chester was saying, which is, what do they really need to know? Do they need to know all the technical skills of a math major who's going to go on to other math courses? Could we scale back on some of that and work more deeply? And finally, do the other departments want them to be doing this? Again, I don't know, but I do think in some conversations I've had with other departments along with Peter, is when we were designing a course, was that they really want them to be developing these problem-solving skills. And I do think that that is how they would start developing those. So in that sense, I think that it is somewhat wanted.
Is this, we move down the line, or can I kind of jump in?
Jump.
Is that okay? So I think this point is valid. And I just want to draw everyone's attention to this wonderful diagram that's been sitting there. I mean, it's a volume of revolution diagram. In fact, I came in today thinking this is a great example that, you know, even a math major, where's the application of a volume of revolution using integration to compute something like that? You know, it's a nice application to practice integration on. But, you know, to a chemist, to a physicist, do we need to think about that? It's important to think about three-dimensionality in general, but maybe that's not a very important topic that needs to be focused on, and just the understanding of what an integral is. It's adding things, right? Getting more to the likely application of probability and statistics.
Okay, to kind of connect to this, I want to say, so one reason why this is important is because it develops our students three-dimensional, so intuition about three-dimensional space. Why is that important? Because, for instance, if you apply to be a dentist, that's one of the most important things. Your ability to judge, so you have a mouth, you shouldn't be missing a tooth and drilling somebody's tongue or something like that, right? So spatial knowledge, spatial intuition is actually extremely important. And this is one thing I wanted to say. So when we teach mathematics, we're teaching a lot more than that, right? So if you teach integration, you're teaching a lot more than just summation, or you're teaching a very rich topic, which requires lots of reasoning, lots of thinking. One other thing about other departments, and in my experience, and I have many examples, my answer is they do not care. So some time ago, when I was undergraduate chair, there was an initiative to move math for engineering courses into engineering department. Why? Because we said, okay, you guys know best what is needed. Do you know what they said? Well, they said, no, what you're doing is good. We don't want to do anything with it. Okay. Well, chemistry wasn't happy with our math courses, so they designed their own math for chemists course, which died after a few years, and now the students are back to us. So in many, many ways, so here's another example. I created a course which is called Numbers for Life. Numbers for Life is a course for all those people who do not really need serious math, but would like to see how math is really used. So things we discuss, for instance, are, well, how do you compute interest on a credit card? Or just knowing that there is interest on a credit card. We talk about economic indicators. We talk about financial things. We make estimates. So what will happen if the temperature of the oceans increases by 1 degree? How higher up are oceans going to be? And then we realize, well, we can compute that actually the airport in Vancouver will be underwater, stuff like that. Now, the good and bad news about this is that if you want to have such a course, all you need is up to grade 10 math. You don't even need functions. You don't even need integration, calculus, any of that stuff. It is amazing how much you can do and how much stuff in real life is done just by using elementary mathematics. Okay, so now my final point is this. So if we talk against calculus, okay, in preparation for this, I examined a book on microeconomics microeconomics, macroeconomics, and also in modeling in economics. 95% of mathematics there are graphs and relations between several graphs, points of intersection, looking at heights, areas, stuff like that. Not a single formula. So this is not, here's a formula, produce a graph. All those graphs were derived from data. That's not what we do in calculus. So instead of giving our students a diagram, we should tell them, okay, or ask, how was the diagram created? Why does it look like an exponential function, right? Okay, okay. So I'll talk later more.
We have another 5 minutes for you to interact, so challenge your fellow debater.
Well, I will not challenge, I will just concur maybe with Miroslav. It points to the need of better communication, I think, with service departments, finding those who care and working with them to really find the mathematical needs for the students to be successful in their programs, to understand the relevance of what they learn as they learn the mathematics in preparation for their program. So maybe it's finding those who care and who will want to make a change, who will want to make a difference. So I'm not contradicting you. See, I'm supporting you. Yes.
Okay, thank you. Yeah.
Yeah, I think we're in agreement too much for a debate. I think when I was making my own notes, I mean, I have it circled on my page, and sort of the leading point was to communicate, right? It's not up to, I think, you know, my opinion is that it's not up to the math department to decide what the other departments need in their service courses. But communication, as long as there is communication, can lead to designing things that work. We've got 3 or 4 different calculus classes. Business, one for health sciences, biology, then math majors and others go through one for the first term. After that, we've got 2 different intro to proof courses, okay? One smaller one for math majors, and then a larger one for computer science mostly and others. And then recently, just first time rolling it out this year was a new linear algebra course, which does not use the word basis. Still has a lot of the same theory that you're able to kind of go through without spending hours on technicality. But instead of hours on technicality, the time is spent motivating with actual examples, like looking at Google PageRank and how linear algebra comes into play there, applications of eigenvalues and eigenvectors, RGB, pixel color, things like that. It's designed mostly for computer science to keep them interested, but also, you know, somewhat applicable. At least they can see the motivation comes from seeing that this might actually be useful as we move forward, even though we have to spend a little bit of time on that beautiful theory, short amount of time.
Could I ask a quick question? Is so kind of going back to what Miroslav said about the courses being interchangeable. Is a calculus course like that, does it need to be interchangeable with your linear algebra, sorry, with your other linear algebra courses?
Yeah, and that's the question that we're trying to figure out, because they do, in fact, the math major linear algebra and the non-math major linear algebra, they're both suitable prerequisites for our second single linear algebra course that mostly only math majors would end up going through. So we are figuring that out, but again, we've got people who are interested and motivated to figure it out. So we know what not to spend time on in the first one, knowing that it is going to be covered in the second one, for instance. But the idea of not having the word basis in the first course is that's the biggest challenge right now.
That's what came to my mind.
Actually, kind of one anecdote about service courses. It was a video I watched. So there was a kid I think starting university, who was interested in designing video games. And basically that kid, so they recommended that he takes a first year linear algebra course. Do you think that course will actually motivate him? So learning about independence, eigenvectors, diagonalization, 75 equivalent statements about regular matrices. Is that going to motivate this kid to learn more, to design video games, or is he going to just give up? Right. See, my point is that in spite of the fact that we failed to do that, we have to reach out to the other side. That's what we all say, but in a sense where we have to be more drastic. Well, we should tell them, well, listen, we'll stop teaching your kids. Of course, we cannot do that because it brings us money, right? But in theory, that's what I would like to do. Okay, you engineers, you know best what you need, so teach math to your kids. And by the way, don't call it service course. Teach your math within your engineering courses, within your physics courses. See, I was educated in Europe, which was slightly different, but here is one thing. Where did I learn about gradient and divergence and curl? In physics course, because it was needed there. They derived it based on physical intuition, which was much better than this dry stuff that you teach when you teach second calculus, for instance, at McMaster, right? So, sorry? Yeah, well.
Okay.
So just to finish this, in many ways, I'm pessimistic because, see, university is like a huge elephant that you have to push uphill. You cannot do that. Every change takes forever to make. And I agree that I can communicate with engineering, but communication has to escalate to the levels of deans. And once you do to the level of deans, everything is killed because I was busy with something else and never with your problems. Okay? So I'm not optimistic. And if you are here and alive 10 years from now, we'll probably discuss the exactly same things. And this is what kind of what makes me really pessimistic about the whole thing.
I will now disagree.
Okay.
with
Then
Miroslav.
I'll disagree with you then after that.
Good. I don't think that the solution to give the courses to the service departments is a good one. I think we have something to bring to this, to deciding what is the math that should be, how, the what and the how we should be teaching the math for the students. I think we're not the sole decision makers. We should not. I think it's a conversation that should take place. Just pushing it away, you know better, I would disagree. I think that that would not be a solution. Also for the survival of departments, it does bring money as well. And I would like to disagree to another previous idea that was mentioned about the authentic examples. In my anecdote that I mentioned earlier, where the examples come from the service departments, is one way to go look for authentic example. You could doubt, you could say, well, are they really authentic? I want to rely on the service departments to give me these examples. Maybe they are not authentic in the professional world in that way, but they could be, this is what is used in their program of studies, and they should encounter that kind of examples later, and that should help the students to see the relevance of the math for their studies. Ideally, they are authentic examples. So it goes beyond just the studies, it goes to really their future career. But again, I would like to rely on the service departments to provide that kind of examples. And I would argue that we do have that kind of examples.
Yes, but reality, I mentioned I was working on the life sciences textbook. Among other things, I examined textbooks in biology. And what I found really alarming is the fact that the textbook authors made every possible effort to avoid mathematics. Pick any biology course, even where there was obvious that you could do some math, it is not there. So this is the problem, right? I mean, the problem is that, of course, we know that math is there, right? But does the other side know, and does the other side appreciate, right? In case of biology, the answer is no. Of course, we have courses for math biology offered by math department. We have math modeling course offered by math department where we do these applications. But you would expect the other side to at least appreciate and use it where it's obvious, rather than awkwardly avoid discussing things which are quantitative in nature.
Thank you, Miro. Let's end it on a serious note.